Right now, you are experiencing reality. Or at least, you think you are. The ground beneath your feet, the screen in front of you, the air you breathe, all of it feels solid and undeniably real. But what if none of it actually exists in the way you assume? What if your entire universe, every star, every atom, every thought you've ever had, is nothing more than information running through a cosmic computer? This isn't science fiction anymore. It's a serious question being asked by physicists, philosophers, and mathematicians around the world. The simulation hypothesis suggests that we might be living inside a computer program, that reality itself could be artificial. And the evidence supporting this idea comes from the strangest place imaginable, the fundamental laws of physics themselves. In 2003, philosopher Nick Bostrom published a paper that would change how we think about existence. His simulation argument presented three possibilities, and at least one of them must be true. Either civilizations like ours always destroy themselves before developing the technology to create realistic simulations, or advanced civilizations choose not to run such simulations, or we are almost certainly living in one right now. The logic is deceptively simple. If future civilizations can create even one perfect simulation of reality, they would likely create thousands or millions of them. Which means simulated minds would vastly outnumber real ones. Do the math. If there are 1,000 simulated realities for every base reality, you have a 99.9% chance of being in a simulation. You're probably not that lucky. Elon Musk famously stated there's only a 1 in billions chance we're in base reality. He pointed out that video games have evolved from pixelated blocks to photorealistic worlds in just 40 years. Where does that trajectory lead in another 1,000 years? In another million? The progression seems obvious. Games become indistinguishable from reality, and at that point, the distinction between simulation and reality collapses entirely. But this raises an immediate question. If we're in a simulation, wouldn't there be evidence? Wouldn't we find glitches, errors, or computational shortcuts in the fabric of reality itself? Here's where physics gets unsettling. Quantum mechanics, the most successful theory in the history of science, describes reality in ways that are eerily similar to how a computer program would function. Take the double-slit experiment, first performed in 1803 by Thomas Young. Fire a single photon at two narrow slits, and it behaves like a wave, creating an interference pattern as if it went through both slits simultaneously. That's strange enough. But add a detector to see which slit the photon actually passes through, and the interference pattern vanishes. The photon suddenly behaves like a particle, going through just one slit. The act of observation changes reality. Richard Feynman, who won the Nobel Prize in Physics, called this the central mystery of quantum mechanics. The universe doesn't seem to render information until it's observed. Particles exist in multiple states at once, a phenomenon called superposition, until the moment you measure them. Then they collapse into a single definite state. It's exactly how a video game works. The computer doesn't process the entire game world simultaneously. It only renders what you're looking at. Turn your character around, and the computer generates that view. The rest exists in a state of probability, compressed information waiting to be unpacked when needed. This isn't a metaphor. It's a direct parallel to how quantum systems behave. Physicist Thomas Campbell has spent decades exploring this connection. He argues that quantum mechanics isn't just describing particles, it's revealing the architecture of reality itself. Superposition, entanglement, the uncertainty principle, these aren't quirks of nature. They're features of an information-based system. Campbell suggests that what we call physical matter is actually rendered information, much like pixels on a screen. The universe computes what it needs to show you in the moment, and nothing more. You might think this sounds too convenient, too much like forcing physics to fit a preferred conclusion. Except the evidence doesn't stop there. It gets stranger. Reality appears to be pixelated. At the smallest scale, the universe is quantized. There's a minimum unit of length called the Planck length, approximately 1.6 times 10 to the negative 35 meters. Below this scale, the concept of distance breaks down entirely. Similarly, there's a Planck time, the smallest meaningful unit of temporal measurement. You can't divide space or time any further. They're discrete, like the resolution of a digital image. Elementary particles, the building blocks of everything you see, come in discrete units. Electrons don't have half charges or fractional spins. Energy exists in packets called quanta. Even the constants that govern physics, the speed of light, Planck's constant, the gravitational constant, are fixed values. They don't vary. They're locked in, like parameters in a simulation's code. This is exactly what you'd expect if reality were computational. Any simulated universe would need a resolution limit. You can't have infinite precision in a finite system. The Planck scale would represent the smallest grid size the simulation can process, the fundamental pixel of spacetime itself. But there's a problem with this picture, one that recent research has highlighted. In November 2025, researchers at UBC Okanagan published findings that challenged the entire simulation hypothesis. Using Gödel's incompleteness theorem, they demonstrated something profound. The universe requires what they call non-algorithmic understanding, something no computation can replicate. Any simulation is algorithmic by definition. It follows programmed rules, deterministic or probabilistic operations that can be expressed mathematically. But if the fundamental nature of reality depends on understanding that exists beyond algorithms, then a simulation cannot capture it. The research proves it's impossible to create a physically complete theory of everything through computation alone. Quantum gravity, the holy grail of physics that would unite general relativity with quantum mechanics, cannot be derived from computational principles. There's something deeper, something more fundamental than the computational laws we observe. And that means the universe cannot be a simulation in the way Bostrom described. This creates a fascinating tension. On one hand, quantum mechanics behaves exactly like a computer program. On the other hand, mathematics tells us reality can't be computed. So what's actually going on? Perhaps the answer lies in reframing the question entirely. What if we're not asking whether reality is a simulation, but what reality fundamentally is? The physicist John Archibald Wheeler proposed that the universe is made of information, with matter and energy as secondary phenomena. His famous phrase, "it from bit," suggests that physical existence emerges from information processing. This isn't the same as saying we live in someone else's computer. It's saying the universe itself is computational in nature, not because it was programmed, but because information processing is the deepest layer of existence. Jacob Bekenstein expanded on this in 2003, arguing that thermodynamic entropy and information entropy are equivalent. The disorder in a physical system directly corresponds to the amount of information needed to describe it. When you burn a book, you're not destroying matter, you're scrambling information. The atoms still exist, but the meaningful arrangement is lost. Bekenstein showed that a black hole's entropy is proportional to its surface area, not its volume. All the information about everything that falls into a black hole is encoded on its event horizon, a two-dimensional boundary. This led to the holographic principle, one of the most radical ideas in modern physics. Proposed by Leonard Susskind and Gerard T. Hooft, it suggests that our three-dimensional universe might be a hologram, a projection from information encoded on a two-dimensional surface at the edge of spacetime. Juan Meldacena provided mathematical proof for a specific version of this in 1997, showing that a five-dimensional universe with gravity can be perfectly described by a four-dimensional theory without gravity. The interior and the boundary are equivalent, two ways of describing the same reality. If this applies to our universe, it means everything you experience, every depth, every distance, every solid object, is a projection. The true reality exists as information on a distant cosmic screen, and what you perceive as three-dimensional space is the hologram it generates. Think about that for a moment. You're not inside the universe. You're being projected from its boundary. The holographic principle solves several problems in physics, particularly the black hole information paradox. But it also raises new questions. If the universe is a hologram, where is the projector? What is reading the information and creating the projection we experience? Some physicists argue there is no projector, that the holographic description and the three-dimensional description are simply two equivalent ways of talking about the same thing. Others suggest consciousness might play a role, that observation isn't just revealing reality but actively participating in its construction. This brings us back to quantum mechanics and the observer effect. Particles don't have definite properties until measured. The universe doesn't seem to commit to a specific configuration until someone looks. In the double-slit experiment, the photon doesn't choose a path until you check. It's as if reality waits for conscious observation before finalizing the details. The physicist Eugene Wigner took this seriously. He proposed that consciousness collapses the quantum wave function, that mind and matter are fundamentally connected. Most physicists reject this interpretation, but no one has a better explanation for why observation matters. The equations work. The predictions are accurate. But why measurement changes reality remains one of the deepest mysteries in science. What if the answer is that reality is information, and consciousness is the process that interprets it? This would mean we're not in a simulation created by someone else. We're in a reality that is inherently informational, and our minds are part of the system that makes it real. The universe doesn't exist in a definite state until it's observed, because observation is what transforms potential information into actual experience. The self-simulation hypothesis takes this even further. It suggests the universe might be simulating itself, a strange loop where reality creates the conditions for consciousness, and consciousness observes reality into existence. There's no external programmer. The system is self-referential, generating itself through its own internal logic. Dreams provide an interesting analogy. When you dream, you create an entire world, complete with physics, characters, and narratives. You experience it as real while it's happening. The resolution can be incredibly high, the details vivid and convincing. Yet it's all generated by your mind, a biological information processor running on neural networks. If consciousness can create realistic simulations internally, perhaps the universe is doing something similar at a cosmic scale. But these ideas, as fascinating as they are, don't answer the practical question. How would we know? If we are in a simulation, whether external or self-generated, there should be ways to test it. Physicist John Barrow suggested that simulations would accumulate computational errors over time, requiring periodic corrections. We might observe these as sudden changes in physical constants or contradictory experimental results. So far, measurements of fundamental constants like the fine structure constant show no variation over billions of years. Either the simulation is error-free, or we're not in one. In 2012, physicists Silas Bean, Zara Davuti, and Martin Savage proposed a different test. They argued that a simulated universe would have to discretize spacetime, creating a lattice structure. High-energy particles would interact with this lattice, producing specific signatures that could be detected. They suggested looking for anomalies in cosmic ray patterns. The results have been inconclusive so far. Thomas Campbell has proposed laboratory experiments to test whether quantum systems behave as if they're being rendered on demand. These experiments examine whether quantum effects in the double-slit experiment and quantum eraser setups show signs of computational optimization. If reality is rendered only when observed, there should be measurable differences between observed and unobserved quantum systems beyond what standard quantum mechanics predicts. The challenge is that any evidence we find would be internal to the system. If we discover the universe is pixelated, is that proof of simulation or just a fundamental property of spacetime? If we find glitches, how do we know they're not just new physics we don't understand yet? The simulation hypothesis is difficult to test because we can't step outside the system to verify it. This is where David Wolpert's recent mathematical framework becomes crucial. Wolpert, a professor at the Santa Fe Institute, approached the question rigorously. Instead of treating universes as mysterious physical systems, he modeled them as computers. This lets him apply computational theory directly to the simulation question. Using Kleen's second recursion theorem, which describes how a program can generate an exact copy of itself, Wolpert showed something unexpected. If one universe can simulate another, then that simulated universe can simulate the first one back. There's no hierarchy. You can have closed loops of universes simulating each other. You can have infinite chains. And most strangely, you can have multiple versions of the same person existing across different simulations, all of whom are mathematically the same individual. This framework reveals that many common assumptions about simulations break down under rigorous analysis. The idea of a base reality becomes ambiguous. If simulations can loop back on themselves, which one is real? Perhaps none of them are. Or perhaps they all are, each one as valid as any other. Wolpert's mathematical framework reveals something that sounds like science fiction but follows inevitably from the logic. If you can simulate me, I can simulate you back. The hierarchy collapses. There's no privileged position, no ultimate basement level where everything originates. Reality becomes a network of simulations, each one as legitimate as any other. This creates an identity problem that philosophers have struggled with for decades. If there are multiple versions of you across different simulation layers, which one is the real you? Wolpert's mathematics suggests they're all equally real. Each copy has the same claim to being you because they're mathematically identical. Your consciousness, your memories, your experiences exist in each instance. There's no original to point to. The implications extend further than personal identity. If simulations can form closed loops, causality itself becomes circular. Universe A simulates Universe B, which simulates Universe C, which simulates Universe A. What caused what? The traditional notion of cause and effect requires a linear timeline, a sequence where earlier events produce later ones. In a loop, that breaks down completely. Now consider the computational requirements. To simulate even a small region of spacetime at the Planck scale requires staggering resources. The Planck length is about 1.6 times 10 to the negative 35 meters. The Planck time is about 5.4 times 10 to the negative 44 seconds. These aren't just small numbers. They represent the fundamental pixels of reality, the smallest meaningful divisions of space and time. Simulating 1 cubic meter of space at Planck resolution for 1 second would require tracking approximately 10 to the 105 discrete units. That's more states than there are atoms in the observable universe. And that's just 1 cubic meter for 1 second. The visible universe contains about 10 to the 80 atoms spread across billions of light-years. The computational demand scales exponentially. In 2017, researchers at Oxford calculated that classical computers cannot simulate quantum mechanics efficiently. The number of variables explodes too quickly. Quantum systems exist in superposition, simultaneously occupying multiple states until measured. Tracking all possible states of even a modest quantum system overwhelms classical computation. Could quantum computers solve this problem? They handle superposition natively, storing information in qubits that exist in multiple states at once. In principle, a quantum computer could simulate quantum mechanics more efficiently than a classical one. But there's a catch. Quantum computers still face fundamental limits. They can't violate the laws of thermodynamics. They can't process information faster than light allows. They're still bound by physics. Here's where things get interesting. If our universe is a simulation running on a quantum computer, that computer must exist in a parent universe with its own physical laws. Those laws would constrain what the simulation can do. But we've never observed such constraints. Our physics appears complete within itself. There are no external limitations we can detect. Frank Wilczek, a Nobel Prize-winning physicist, points out another problem. The laws of physics contain hidden complexity that serves no apparent purpose in a simulation. Quantum field theory includes mathematical structures so intricate they seem wasteful for a computational model. The standard model has 19 free parameters that must be fine-tuned to incredible precision. Why would a simulation include such baroque detail? One answer is optimization. Perhaps reality only renders what's being observed, saving computational resources. This connects directly to quantum mechanics. Particles exist in superposition until measured. The universe doesn't commit to a definite state until something looks. That sounds exactly like a rendering optimization in a video game, where distant objects aren't fully calculated until the player approaches them. The double-slit experiment demonstrates this starkly. Fire electrons one at a time through two slits. Without observation, they create an interference pattern as if each electron passes through both slits simultaneously. Place a detector at the slits to see which path the electron takes. The interference pattern disappears. The electron behaves as if it went through only one slit. The act of observation changes the outcome fundamentally. Thomas Young first performed this experiment with light in 1803, proving light behaved as a wave. Later experiments with electrons showed the same effect. It wasn't a property of light specifically. It was something deeper about reality itself. Richard Feynman called it the central mystery of quantum mechanics. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, says that quantum systems don't have definite properties until measured. The electron isn't secretly going through one slit or the other. It genuinely exists in a superposition of both paths. Measurement forces reality to choose. The wave function collapses. But what counts as measurement? Does it require a conscious observer? A recording device? Any interaction with the environment? The answer remains unclear after a century of debate. Some interpretations, like the many worlds theory, avoid the problem by saying all possibilities occur in parallel universes. Others, like pilot wave theory, restore determinism by adding hidden variables we can't observe. The simulation hypothesis offers a different perspective. If reality is computed on demand, observation triggers the calculation. Before you look, the system maintains a probability distribution. After you look, it commits to a specific outcome. This matches the behavior we observe without requiring consciousness or parallel universes. Thomas Campbell has designed experiments to test this directly. His approach looks for statistical signatures that would appear if reality optimizes its rendering. If the universe only fully calculates observed quantum systems, there should be measurable differences between watched and unwatched experiments beyond standard quantum predictions. The results remain preliminary, but the methodology is sound. The challenge with all these tests is that any evidence we find operates within the system. Suppose we discover spacetime is discrete, built from Planck-scale pixels. Does that prove we're in a simulation, or is it just how spacetime fundamentally works? If we detect glitches or anomalies, are they bugs in the code or new physics we haven't understood yet? We can't step outside to check. This brings us back to the November 2025 research from UBC Okanagan. The team used Gödel's incompleteness theorem to argue that reality cannot be algorithmic. Gödel proved that any sufficiently complex formal system contains true statements that cannot be proven within that system. The researchers extended this to physics, claiming that a complete description of reality requires non-algorithmic understanding. Their argument goes like this: any simulation must follow programmed rules. Rules are algorithms. Algorithms are formal systems. Gödel's theorem applies. Therefore, a simulation cannot capture all aspects of reality. There will always be truths about the system that the system's own rules cannot derive. Reality must be based on something more fundamental than computation. This represents the strongest mathematical challenge to the simulation hypothesis yet. If correct, it means the universe cannot be simulated by any computer, no matter how powerful. The simulation hypothesis doesn't just face practical limitations. It faces logical impossibility. But does Gödel's theorem really apply to physical systems? The theorem concerns formal mathematical systems, not the physical universe. Physics might not be a formal system in the relevant sense. Or perhaps the theorem's limitations don't matter. A simulation doesn't need to be perfectly complete. It just needs to be convincing enough that inhabitants can't tell the difference. Here's another angle. Information theory suggests the universe might be fundamentally made of information rather than matter and energy. Jacob Bekenstein and John Archibald Wheeler argued that physical properties emerge from information. Matter and energy are ways information arranges itself. This doesn't require a simulation in the traditional sense, but it does suggest reality has a computational structure. The holographic principle takes this further. Developed from black hole thermodynamics, it proposes that all information in a three-dimensional region can be encoded on its two-dimensional boundary. The volume is redundant. Everything happening inside can be described by information on the surface. Leonard Susskind described our universe as a hologram, projected from information encoded at its edges. Juan Meldacena demonstrated this mathematically with AD-SCFT correspondence. A five-dimensional universe with gravity can be perfectly described by a four-dimensional quantum field theory without gravity on its boundary. The interior and boundary are equivalent descriptions of the same system. You can calculate what happens inside by working entirely with the surface equations. This is a genuine hologram. The three-dimensional world we experience emerges from two-dimensional information. Not metaphorically. Mathematically. The equations work. Physicists use this correspondence as a tool to solve difficult problems in quantum gravity by translating them into boundary calculations. If our universe is holographic, what does that mean for the simulation question? It changes the computational requirements dramatically. Instead of simulating every Planck volume in three-dimensional space, you only need to track information on a two-dimensional surface. The reduction in complexity is enormous. A holographic universe might be simulatable where a fully three-dimensional one is not. But there's a conceptual problem. If the universe is holographic, which is real, the three-dimensional interior we experience, or the two-dimensional boundary that encodes it, according to the mathematics, they're equivalent. Neither is more fundamental. They're dual descriptions of the same thing. This duality appears throughout modern physics. Different mathematical frameworks describe identical physical situations. Which description is correct? Both are. Or neither is. They're tools we use to make predictions, not ultimate reality itself. The map isn't the territory, but we only ever have maps. Perhaps we're asking the wrong question entirely. Instead of asking whether reality is simulated, we should ask what simulation even means when the simulated and the simulator might be the same thing. David Wolpert's mathematical framework forces this issue. He treats universes as computational systems. Any physical process becomes, in principle, a program. This reframes everything. The simulation question becomes purely computational. Mathematics sets the boundaries, not speculation. Wolpert draws on Kleen's second recursion theorem. A program can generate an exact copy of itself. Extend this to entire universes. If some universe can simulate ours accurately, nothing prevents our universe from simulating that universe in return. Mutual simulation becomes possible. Universe A simulates Universe B. Universe B simulates Universe A. Both are real. Both are simulated. The distinction collapses. This opens stranger possibilities. Infinite chains of simulated universes. Universe contains computer. Computer simulates universe. That universe contains computer. Computer simulates universe. Forever downward. Or closed loops. Universe A simulates B. B simulates C. C simulates A. A circle of causation with no beginning. The framework also multiplies identity. Multiple versions of you exist across different simulations. All are you in a mathematical sense. Not copies. Not duplicates. Genuinely you, experiencing different branches of computational reality. Personal identity becomes distributed across simulation layers. But there's a competing framework entirely. The self-simulation hypothesis rejects external simulators. No advanced civilization. No computer in another universe. Instead, the universe simulates itself. Reality as strange loop. Consciousness generating its own substrate. This sounds mystical until you examine the evidence. Dreams. Every night, your mind generates detailed simulations of physical reality. High-fidelity environments. Accurate physics. Convincing sensory experiences. Lucid dreamers report these simulations are often indistinguishable from waking reality. Resolution exceeds current computer graphics by orders of magnitude. Human dreams are more realistic than our best simulations. Consciousness already performs this feat. Why assume simulation requires external hardware? Perhaps the universe is a mental self-simulation. Consciousness doesn't emerge from matter. Matter emerges from consciousness. Information generates experience. Experience generates information. Self-referential loop. This inverts the standard simulation hypothesis. No dualism between simulator and simulated. One system. Self-generating. Self-observing. The universe computing itself into existence moment by moment. Not a program running on hardware elsewhere. A process that creates its own substrate through the act of computation itself. Occam's razor favors this. We know consciousness can generate convincing simulations. We experience it every night. We don't know that external simulators exist. Why multiply entities unnecessarily? Self-simulation requires fewer assumptions. One reality. One process. Consciousness and physics as two aspects of the same computational loop. But does quantum mechanics support this? Consider superposition again. Particles exist in multiple states until observed. Observation collapses the wave function. Why? The Copenhagen interpretation doesn't really explain it. Measurement causes collapse. But what counts as measurement? What makes observation special? Here's where simulation thinking helps. In a self-simulation, unobserved regions don't need full computation. Like a video game rendering only what the player sees. Quantum superposition might be the universe's way of not computing unnecessary details. Multiple potential states remain unresolved. Observation forces resolution. The system computes what's needed when it's needed. This explains the double-slit experiment differently. Fire electrons one at a time through two slits. They create an interference pattern. Wave behavior. Now observe which slit each electron passes through. The interference pattern disappears. Particle behavior. The act of observation changes the result. Standard interpretation says measurement collapses the wave function. But why? Simulation perspective offers clarity. When unobserved, the system doesn't compute definite trajectories. It processes probability distributions. Waves. Observation requires computing specific values. The system resolves superposition because computation demands it. Not mysterious. Efficient. Thomas Campbell takes this further. He argues quantum mechanics reveals deep computational truths about reality. Superposition, entanglement, uncertainty. These aren't strange properties of matter. They're signatures of how reality processes information. The universe computing itself through consciousness. Entanglement especially. Two particles become correlated. Measure one. Instantly know the state of the other. Distance doesn't matter. Faster than light. No. Information doesn't travel. The correlation already exists in the computational structure. Measuring one resolves both. Like reading two bits from the same register. No communication needed. They're aspects of the same informational state. This suggests something profound. Space and time might be emergent properties, not fundamental. The computational structure underneath doesn't have distance or duration. Those arise from how information organizes itself. Quantum mechanics shows us the seams in spacetime. Places where the underlying computation becomes visible. But here's the critical question. Does any of this prove we're in a simulation? Not really. It shows reality has computational structure. It demonstrates information plays a fundamental role. It suggests consciousness and physics are deeply connected. But simulation? That term might not even apply. When the simulator and simulated merge into one self-generating system, what does simulation mean? When multiple computational descriptions are equally valid, which is the simulation and which is real? When consciousness generates reality which generates consciousness, where's the boundary? Maybe we're not in a simulation. Maybe we are simulation. Not simulated beings in a computer. Not software running on hardware. But a self-computing process that generates both mind and matter as aspects of its operation. Reality as ongoing computation. Computation as reality itself. This removes the need for external creators. No advanced civilization required. No computer in another universe. No base reality somewhere else. Just this. A universe that computes itself into existence through the act of being observed by conscious agents who are themselves computed by the universe. Strange loop. Recursive causation. Self-simulation. Fine-tuning of physical constants supports this view. Why do fundamental values allow life? Not because external programmers tweaked parameters. Because consciousness and physics co-evolve in the self-simulation. The constants that permit observers are the constants that get computed. Observer-dependent reality. Not designed. Self-organized through computational dynamics. Dark energy provides an example. Theory predicts it should be vastly stronger. Strong enough to rip apart all structure. Instead, it's incredibly weak. Just enough to allow galaxies, stars, planets, life. Coincidence? Or computational necessity? In a self-simulation, values that permit observers are values that exist. Observer and observed are coupled. The simulation computes conditions for its own observation. This explains fine-tuning without multiverse. No need for infinite universes where most are dead. One universe. Self-computing. The parameters that allow computation are the parameters that emerge. Consciousness and physics as dual aspects of one self-generating process. Not tuned from outside. Self-tuned through recursive causation. Testing this seems impossible at first. How do you test whether reality is self-simulating? But there might be ways. John Barrow suggested looking for computational errors. If reality is computed, errors might accumulate. Physical constants might drift slightly. We should monitor them. Sudden changes would indicate correction. Glitches in the code. Other tests probe computational limits. If space is fundamentally discrete, we might detect it. Cosmic rays should show patterns. Specific energy distributions. Lattice structure in spacetime would affect high-energy particles. Several groups are searching for these signatures. So far, nothing definitive. But the search continues. The double-slit experiment offers another approach. Thomas Campbell designs variations that test whether observation itself drives physical outcomes. Does consciousness collapse wave functions? Or do wave functions collapse themselves? Subtle differences in setup might reveal whether mind plays an active computational role. Results pending. David Wolpert's framework makes different predictions. If universes can mutually simulate, we should find mathematical structures that allow self-reference. Computational systems capable of simulating themselves. Godot-like loops in physics. Self-referential equations that generate their own solutions. Some quantum gravity theories show hints of this. String theory. Loop quantum gravity. Self-referential mathematics at the foundation. But perhaps the strongest test is consciousness itself. If reality is self-simulation, consciousness isn't emergent from matter. Matter and consciousness are aspects of the same computational process. This makes testable predictions. Consciousness should show computational properties. Information processing at the quantum level. Integration of information across brain regions in specific patterns. Giulio Tononi's integrated information theory attempts this. Consciousness correlates with information integration. The more integrated, the more conscious. Measurable in brain activity. Testable in principle. If consciousness is fundamental to reality's self-simulation, we should find computational structures in awareness itself. Early results suggest we do. None of this proves anything conclusively. We're still mapping the territory. But the landscape looks different than expected. Not simulated beings in an external computer. Not purely physical matter following deterministic laws. Something stranger. A self-computing reality where consciousness and physics generate each other through recursive observation and measurement. The simulation hypothesis evolves. From external programmers to self-simulation. From hardware and software to recursive information processing. From asking if we're in a simulation to recognizing we might be simulation itself. The question transforms when you follow the mathematics far enough. Not simulation or reality. Both. Neither. Something that defies the categories we use to make sense of existence itself. This realization forces a complete reframing. We've been asking the wrong question. Not, are we in a simulation, but what kind of process generates experience and physical law simultaneously? The UBC Okanagan research from November 2025 claims to end the debate. They invoke Gödel's incompleteness theorem. Any simulation must be algorithmic. Follow programmed rules. But reality, they argue, requires non-algorithmic understanding. Something computation can't capture. Therefore, the universe can't be simulated. Case closed. Except the conclusion assumes simulation must mean classical computation. Digital processors. Binary logic. That's not what the self-simulation hypothesis suggests. If reality generates itself through observation, through consciousness interacting with quantum possibility, there's no external algorithm. No programmer writing code. The process isn't computational in the traditional sense. It's recursive. Self-referential. Reality computing itself not through predetermined rules but through moment-by-moment actualization of potentials. Consciousness and physics as dual aspects of one bootstrapping process. Gödel's theorem actually supports this. Self-referential systems can't be both complete and consistent within their own framework. They require something outside. Or more accurately, something that transcends the distinction between inside and outside. A strange loop. Exactly what Douglas Hofstadter described in Consciousness Itself. The UBC team proves you can't simulate reality using predetermined algorithms. Agreed. But who said reality uses predetermined algorithms? Quantum mechanics already shows us it doesn't. Superposition, entanglement, measurement collapse. These aren't deterministic processes following programmed instructions. They're probabilistic, observer-dependent, fundamentally open. Here's where it gets interesting. If you accept the UBC argument, you're forced toward either pure materialism or something like the self-simulation hypothesis. Either reality is purely physical, matter and energy following laws we can eventually map completely, or it's something stranger. A self-generating process where physics and experience co-arise. Pure materialism has its own problems. The hard problem of consciousness. Why does subjective experience exist at all? How do neurons firing produce the feeling of being you? Philosophers have wrestled with this for centuries. No purely physical explanation has ever satisfied. You can map brain activity, correlate neural patterns with reported experiences. But the gap remains. Why those physical processes feel like anything from the inside? The self-simulation hypothesis offers a different approach. Consciousness isn't produced by physical processes. It's the other side of the same coin. Reality and awareness as two aspects of one self-computing system. Not matter creating mind. Not mind creating matter. Both emerging together through recursive observation and collapse of quantum possibilities. This sounds mystical. It's not. It's mathematical. David Wolpert's framework shows how universes can mutually simulate each other. No need for external substrate. Systems capable of self-reference. Kleen's recursion theorem extended to physical reality. A program that generates itself. A universe that computes its own existence through the act of observation. You find similar structures in quantum mechanics itself. The Wheeler-DeWitt equation describes the wave function of the entire universe. No external time parameter. The universe doesn't evolve through time. Time emerges from correlations within the universal wave function. Self-referential. Timeless. The universe as a self-contained mathematical structure that generates its own temporal experience. String theory hints at this too. Not through the popular image of tiny vibrating strings but through deeper mathematical structures. M-theory unifies different string theories by revealing them as different perspectives on the same underlying reality. What looks like separate theories are actually aspects of one self-consistent mathematical framework. Reality describing itself from multiple viewpoints simultaneously. Loop quantum gravity takes a similar approach. Space isn't fundamental. Spacetime itself emerges from more basic structures. Spin networks. Quantum geometry. These aren't embedded in space. They are space. Self-generating through quantum relationships. No background. No stage where physics plays out. Physics is the stage. Self-constructing moment by moment. This connects to information theory in unexpected ways. Jacob Bekenstein showed that entropy and information are equivalent. The number of possible arrangements of matter equals the information needed to specify any particular arrangement. Physical systems are information systems. Not metaphorically. Mathematically. Thermodynamics is information theory applied to physical processes. The holographic principle extends this. Juan Meldesena's AD/CFT correspondence shows that a theory with gravity in the interior of space is mathematically equivalent to a theory without gravity on the boundary. Three-dimensional physics encoded in two-dimensional information. The interior and boundary aren't separate realities. They're different descriptions of the same thing, like wave-particle duality but for entire spacetimes. This isn't saying reality is literally a hologram projected from a distant surface. It's saying the information content of any region is fundamentally limited, bounded by surface area, not volume. Why? Because information is the fundamental currency. Matter and energy are secondary expressions of underlying information patterns. Now combine these insights. Reality as self-referential mathematical structure. Physics and consciousness as dual aspects. Information as fundamental. Quantum mechanics showing observer-dependent collapse. The holographic principle revealing dimensional relationships. All pointing toward the same conclusion. Reality isn't simulated by something external. It simulates itself through the process of being observed. But what does that actually mean? How does self-simulation work? Start with quantum superposition. Particles exist in multiple states simultaneously. Not because we don't know which state they're in, because they're genuinely in all states until measured. Measurement forces a choice. Collapses the wave function. One possibility becomes actual. Who or what does the measuring? In standard quantum mechanics, measurement requires a classical observer. Something outside the quantum system. But there is no outside. The entire universe is quantum. So what collapses the universal wave function? The Copenhagen interpretation avoids this by declaring measurement devices classical by fiat. Convenient but unsatisfying. The many worlds interpretation says nothing collapses. All possibilities occur in different branches. Elegant mathematically but ontologically extravagant. An infinity of universes spawned every instant. The self-simulation approach offers a third option. Consciousness itself performs measurement. Not human consciousness specifically. Something more fundamental. The capacity for a system to observe itself. To distinguish between states. This doesn't require neurons or brains. It requires self-reference. Information systems capable of modeling their own states. Giulio Tononi's integrated information theory formalizes this. Consciousness correlates with information integration. The more a system integrates information, the more conscious it is. Not just processing information but unifying it into coherent wholes. Creating distinctions. Generating meaning through relationships. Measured in brain activity, this shows up as specific patterns. Neural regions communicating in synchronized ways. Information flowing across the connectome. The more integration, the richer the conscious experience. Sleep reduces integration. Anesthesia disrupts it. Return of integration accompanies return of awareness. But here's the key insight. If consciousness is information integration, and physics is information processing, consciousness doesn't emerge from physics. They're the same process viewed from different perspectives. Internal experience and external measurement as two sides of one informational coin. This makes testable predictions. If self-simulation is correct, quantum systems should show signatures of self-measurement, not requiring external observers, collapsing their own wave functions through internal information integration. Some quantum eraser experiments hint at this. Results suggesting the quantum system itself determines outcomes before any external measurement occurs. Thomas Campbell designs experiments to probe this directly. Variations on the double-slit setup that distinguish between observer-induced collapse and self-collapse. Subtle differences in timing. In the role of measurement apparatus. In what counts as observation. Results so far are ambiguous. The experiments are extraordinarily difficult. But the theoretical framework is clear. If consciousness plays an active role, specific predictions follow. The fine-tuning problem takes on new meaning here. Why are physical constants so precisely calibrated for life? Not because a programmer set the dials. Because only observer-compatible constants exist in a self-simulating reality. The parameters that allow observation are the parameters that get computed. Anthropic principle not as selection effect but as computational necessity. This explains fine-tuning without multiverse. No need for infinite dead universes. Just one universe self-generating through conditions that permit self-observation. The act of observation and the observed universe co-arising through recursive causation. Not designed. Not random. Self-organized through information dynamics. Dark energy provides a concrete example. Theory predicts it should be vastly stronger. Strong enough to rip apart atoms. Instead, it's extraordinarily weak. Just enough to allow structure formation. Galaxies. Stars. Planets. Observers. In self-simulation, this isn't coincidence. It's computational requirement. The universe computes values compatible with its own observation. Similar logic applies to other constants. The strength of fundamental forces. The masses of particles. The cosmological constant. Each could have been different. But only a narrow range permits complex structures capable of self-observation. In external simulation, this requires fine-tuning. In self-simulation, it's automatic. Observer and observed are coupled through the computational process itself. This transforms how we think about consciousness. Not an accident of evolution. Not an emergent property of complex brains. Something fundamental to reality's self-generation. Without observation, without the capacity to distinguish states and integrate information, the quantum wave function never collapses. Possibilities never become actualities. Reality remains purely potential. Consciousness, in this view, is reality observing itself into existence. Not creating matter from nothing. Actualizing specific configurations from quantum possibility space. The universe as a self-observing system. Physics and awareness as dual aspects of one self-computing process. Human consciousness is just one expression of this. Brains integrate information in particularly rich ways. But information integration happens at multiple scales. Cells. Organs. Ecosystems. Perhaps even fundamental particles. Different degrees of integration. Different intensities of experience. But the same basic process throughout. This doesn't make everything conscious in human terms. A photon isn't thinking about its trajectory, but it does process information, responds to its environment, integrates inputs to determine outputs. Minimal consciousness, but consciousness nonetheless. The universe aware of itself at every scale, in varying degrees, through countless centers of integrated information. If this sounds radical, consider what physics already tells us. Reality at the quantum level doesn't exist in definite states until measured. Space and time aren't fundamental but emerge from deeper structures. Information is conserved. The universe behaves like a self-contained mathematical system with no external reference frame. We're already living in something stranger than classical materialism allows. Self-simulation introduces a recursion problem that makes the concept even stranger. If consciousness generates reality through observation, what generates consciousness? Standard answer: biological evolution produced brains capable of awareness. But that evolution occurred within the reality consciousness supposedly generates. Circular causation. The observer creates the observed, which creates the observer. This isn't a flaw in the logic. It's the point. Reality as bootstrap paradox. Self-causing. Self-sustaining. No external foundation required. Mathematics provides the template. Gödel's incompleteness theorems prove formal systems can't establish their own consistency from within. They require axioms that can't be proven within the system itself. Yet mathematical structures exist independently of proof. Pi exists whether we can prove it or not. Prime numbers follow their pattern regardless of human awareness. Self-simulation suggests reality works similarly. Not provable from within. Not requiring external validation. Simply self-consistent. David Wolpert's framework formalizes this mathematically, treating universes as computational systems, applying computer science theorems to cosmology. The result: if one universe can simulate another, nothing prevents reciprocal simulation. Universe A simulates Universe B. Universe B simulates Universe A. Both are real. Both are simulations. The distinction collapses. Wolpert extends Kleene's recursion theorem to entire realities. In computer science, this theorem shows how programs can generate perfect copies of themselves. Applied to universes, it implies something profound. Self-simulation isn't just possible. It might be necessary. A universe capable of modeling itself must contain the information to do so. That information is the universe. Reflection becomes substance. The map becomes the territory. This creates closed causal loops. Not paradoxes exactly. Strange loops. Systems that define themselves through self-reference. Hofstadter explored this in cognitive science. Consciousness as strange loop. Self-awareness arising from systems complex enough to model themselves. The brain creates a model of the world that includes the brain creating the model. Infinite regress that somehow terminates in subjective experience. Apply that same logic to the cosmos. Universe creates a model of itself that includes the universe creating the model. Infinite regress terminating in physical reality. Observer and observed as dual aspects of one self-referential process. The computational requirements seem impossible. Simulating every particle, every quantum state, every possible outcome. But quantum mechanics already shows nature doesn't compute everything. Only what gets measured. Only what gets observed. Unmeasured particles exist in superposition. Multiple states simultaneously. Computation deferred until observation collapses the wave function. This is exactly how efficient simulation would work. Render only what's being observed. Leave everything else in compressed possibility space. Video games do this. Distant terrain exists as low-resolution approximations. Only the immediate area gets full detail. As you move, computation shifts. Always focusing on the observed region. Nature might use the same strategy. Quantum superposition as computational optimization. Wave function collapse as rendering on demand. The double-slit experiment fits this framework perfectly. Particle behavior changes when observed. Not because observation disturbs the particle. Because observation triggers computation. Without measurement, the particle remains in possibility space. Existing is wave. Potential rather than actual. Measurement forces actualization. The system computes a specific outcome. Renders definite position. Creates classical reality from quantum possibility. Standard quantum mechanics describes this without explaining why. Copenhagen interpretation simply accepts it. Wave function collapse is axiomatic. The math works. The predictions match experiment. But the mechanism remains mysterious. Self-simulation provides mechanism. Reality computes itself. Observation is computation. Consciousness is the universe processing information about itself. Each measurement updates the global state. Each observation actualizes previously potential configurations. Physics and awareness as two descriptions of one underlying process. Information integration. Critics point to energy requirements. Simulating quantum systems on classical computers is exponentially inefficient. Oxford researchers showed it's essentially impossible. The computational resources exceed anything achievable. But that critique assumes classical computation. Quantum computers change the equation. They don't just simulate quantum mechanics. They instantiate it. A quantum computer processing quantum information isn't simulating physics. It's doing physics. The distinction between simulation and reality dissolves. If the universe is a quantum computer computing itself, asking whether it's simulated becomes meaningless. It's not being simulated elsewhere. It's self-computing. Process and product identical. The universe is quantum algorithm running on quantum substrate. That substrate is the universe itself. Not turtles all the way down. One turtle. Self-supporting through recursive self-reference. Recent research from UBC Okanagan challenges this from a different angle. Using Gödel's incompleteness theorem to argue reality requires non-algorithmic understanding. Something beyond computation. The proof is elegant. Any algorithm follows programmed rules. Makes deterministic or probabilistic choices based on predefined logic. But quantum mechanics shows nature doesn't behave this way. Wave function collapse isn't algorithmic. It's not following a program. Measurement outcomes are genuinely random. Not pseudo-random. Not deterministic but unpredictable. Truly random. irreducible to algorithm. If that's correct, simulation is impossible. Not just technically difficult. Mathematically impossible. No algorithm can reproduce genuinely random processes. No computation can capture non-algorithmic understanding. Reality must be more fundamental than computation. Spacetime itself emerging from something deeper. Something that can't be reduced to bits and operations. This shifts the question. From whether we're simulated to what makes simulation impossible. What is this non-algorithmic understanding? Where does it exist? How does it generate reality? The researchers argue it's more fundamental than spacetime. More basic than quantum fields. The substrate from which physics emerges. Call it proto-consciousness. Not awareness in human terms, but something with the capacity to distinguish states, to integrate information, to collapse possibility into actuality. The thing that makes wave function collapse happen. Not following an algorithm. Not computing outcomes. Simply choosing. Actualizing. Making reality real. This loops back to observation. But now observation isn't computation. It's something more fundamental. The basic capacity of reality to be in definite states. To have actual properties rather than just potential ones. Consciousness in this view isn't what brains do. It's what reality does. Brains just do it in particularly complex and integrated ways. Creating rich inner worlds. Self-models. Subjective experience. But the basic process, actualizing the potential, happens everywhere. Every quantum measurement. Every wave function collapse. Every moment of definite reality. If this is right, we're not in a simulation because simulation is impossible. Reality is self-generating through non-algorithmic process. Not computed. Not programmed. Self-organizing through principles we don't yet understand. Gödel's theorem becomes cosmological principle. Just as formal systems can't prove their own consistency, reality can't be derived from computation alone. Something more fundamental is required. That something is already here. Already operating. The universe existing through its own non-algorithmic nature. Making itself real moment by moment through processes that transcend algorithm. The debate isn't settled. Self-simulation advocates argue non-algorithmic doesn't mean non-computational. Quantum computation is non-algorithmic in relevant sense. Truly random. Not reducible to classical program. Yet still computational. Still information processing. The universe as quantum computer wouldn't violate Gödel's theorem. Because quantum computation transcends classical algorithmic limits. It accesses genuinely random processes. Integrates non-computable elements. Operates beyond classical computational boundaries. Maybe that's the answer. Reality is computational but not algorithmic. Processing information but not following program. Self-organizing through quantum information dynamics that include irreducible randomness. Computation plus something more. Algorithm plus non-algorithmic understanding. The marriage of structure and spontaneity generating everything we experience. Either way, the picture emerging is strange. Classical materialism assumed reality existed independently. solid objects in absolute space, deterministic laws governing predetermined outcomes. That view is dead. Quantum mechanics killed it. What replaces it is far more mysterious. Reality as information structure. Not matter. Not energy. Patterns. Relationships. Differences that make differences. Wheeler proposed it decades ago. It from bit. Everything physical arising from binary choices. Yes or no. 1 or 0. Existence or absence. Information as primary. Matter as derivative. This view has gained traction. Quantum information theory treats physical systems as information processors. Black holes as maximum information storage. Entropy as missing information. The universe computing itself into existence through information dynamics. But what processes information? Who reads the bits? Classical computation needs hardware. Silicon chips. Electrical currents. Physical substrate executing logical operations. Where's the substrate for cosmic computation? One answer: the universe is its own substrate. Self-processing. Information processing information. No external computer needed. Reality as recursive loop. Each state generating next state. Past determining future through quantum evolution. The universe as quantum computer using itself as memory, processor, and output. Strange loop of self-reference. Reality bootstrapping into existence. Another answer flips the question entirely. Maybe consciousness doesn't emerge from computation. Maybe computation emerges from consciousness. Panpsychism suggests awareness is fundamental property, not produced by brains. Present everywhere. In particles. In fields. In spacetime itself. Brains just organize it into complex forms. Create integrated experience. Self-awareness. But basic awareness exists at every level. Electrons choosing which slit to pass through aren't computing. They're experiencing. Making primitive choices. Actualizing potential through proto-conscious process. This sounds mystical until you examine alternatives. If consciousness emerges from computation, we need explanation for how. How do electrons and quarks following equations produce subjective experience? The hard problem of consciousness. Why does information processing feel like something? Why isn't it just dark? Mechanical. Empty. Computation in computers doesn't produce awareness. No matter how complex. No matter how integrated. Something else is required. Either consciousness is fundamental and computation emerges from it, or they're both fundamental and interact mysteriously. Or consciousness is illusion and nothing actually experiences anything. That last option is incoherent. You can't doubt experience itself. Descartes got that right. Thomas Campbell runs experiments testing whether reality behaves like simulation. Double-slit variations. Quantum eraser setups. Looking for signatures of rendering. Of observation-dependent reality generation. If universe only computes what's measured, experiments should show it. Delayed choice experiments already hint at this. Particle seems to know whether it'll be measured. Adjusts behavior retroactively. Not traveling through time. Just reality being flexible about what's actual versus potential until measurement forces choice. Campbell's results aren't conclusive. Some experiments show expected quantum behavior. Others show anomalies. Statistical variations. Patterns suggesting reality responds to observation in subtle ways. But quantum mechanics predicts this anyway. Observer effect is built into Copenhagen interpretation. Whether that makes reality simulation or something stranger remains open. The experiments continue. Better equipment. Tighter protocols. Searching for definitive signature. Some glitch that reveals underlying code. So far, reality passes every test. Behaves exactly as quantum mechanics predicts. Which is weird enough without simulation hypothesis. Testing through cosmic rays provides different approach. Bean, Davudi, and Savage proposed checking for lattice structure. If spacetime is discretized, simulated on grid, cosmic rays should show directional bias. Like pixels on screen. Patterns in particle distribution revealing underlying structure. They calculated what to look for. Specific energy cutoffs. Directional asymmetries. Observable signatures of discretized spacetime. But Planck scale lattice might be too fine. Beyond detection limits. Or cosmic rays might not reveal it. Method assumes classical simulation on discrete grid. Quantum simulation wouldn't necessarily have those signatures. John Barrow suggested looking for changing constants. If simulators patch bugs, physical constants might shift. Slightly different values across time. We monitor constants carefully. Speed of light. Fine structure constant. Gravitational constant. So far, they're stable. Within measurement precision. If they changed, we'd notice. Unless changes are too subtle. Too gradual. Or happen during our downtime. When nobody's measuring. That gets paranoid quickly. Any evidence absence becomes evidence of clever simulation. Unfalsifiable. Frank Wilczek points out unnecessary complexity. Laws of physics contain elements that don't seem needed. Hidden mathematical structures. Symmetries that don't affect observations. Why include them in simulation? Why not simplify? Use minimum code necessary. Unless simulators are exploring mathematical structures for own reasons. Not optimizing for efficiency. Or complexity serves purpose we don't grasp. Make simulation more robust. More interesting. More real somehow. But Occam's razor suggests simpler explanation. Reality isn't simulation. It's just complex because mathematics is complex. Laws we discover reflect underlying mathematical necessity. Not arbitrary programming choices. David Wolpert's framework reveals deeper issue. If universe can simulate itself, infinite regress becomes possible. Simulated universe simulates universe that simulates universe. Forever. Which universe is real? Or are all equally real? Kleen's theorem allows self-replication. Program generating exact copy of itself. Extended to universes, you get strange loops. Simulating universes that simulate back. Circular causation. No base layer. No ultimate reality. Just infinite stack of simulations all the way down. And all the way up. This seems absurd. Violates intuition about reality needing foundation. But intuition isn't a reliable guide at these scales. Walpert also reveals identity problems. Multiple U's across simulations. All mathematically identical. All experiencing same thoughts. Which one is you? All of them. None specifically. If perfect copies exist in different simulations, personal identity becomes incoherent. You're not unique instance. You're equivalence class. Set of all identical computational states across all simulations. This challenges notion of individual consciousness. Of being specific person in specific place. Maybe identity is pattern, not instance. The wave, not the particular water molecules. You exist wherever your pattern exists. Multiple places simultaneously. That's already true if multiverse is real. Simulation hypothesis just multiplies it further. Fine-tuning argument supports simulation for some. Constants appear tuned for life. Gravity just right. Electromagnetic force precisely calibrated. Cosmological constant absurdly small. Change any slightly and stars don't form. Chemistry doesn't work. Life impossible. Why this precision? Multiverse explains it through selection. Infinite universes with random constants. We observe life-compatible one because we're alive to observe. Can't observe dead universe. Simulation explains it differently. Constants were chosen. Tuned deliberately. Someone wanted universe capable of producing observers. Either to study evolution of consciousness, or to create ancestor simulation, or for reasons beyond comprehension. But fine-tuning might be illusion. We don't know if constants could be different. Maybe physical necessity determines them. Unique values required by deeper theory. Theory of everything when discovered might show constants aren't free parameters. They're calculated. Derivable from first principles. Then no tuning needed. No selection. No design. Just mathematics being consistent with itself. Or maybe our universe isn't fine-tuned. Just appears that way. Life adapts to whatever constants exist. We think universe is tuned for us. Really, we're tuned for universe. Selection operates on life, not constants. The question shifts. Not whether we're simulated, but what simulation means. If consciousness is fundamental, simulation means something different. Not external computer running code. Reality simulating itself through conscious process. Each observation collapsing wave functions. Actualizing potential. Creating definite reality from quantum foam. Universe self-simulating through infinite acts of measurement. Conscious and unconscious. Every particle interaction. Every wave function collapse. Reality rendering itself into existence moment by moment. This dissolves simulation hypothesis paradox. We're not in external simulation. We're in self-simulation. Reality is simulation, but also real, because simulation and reality aren't opposites. They're same thing. Process of actualization. Potential becoming actual through observation and interaction. Information patterns organizing into coherent experience. Consciousness participating in its own creation. Observer and observed as single process. Whether this helps depends on what you want explained. If question is, are we in matrix-style simulation run by future humans? Answer is probably no. Energy requirements too high. Computational limits too strict. Gödel's theorem too restrictive. If question is reality fundamentally information processing itself into existence? Answer might be yes. But that's not simulation in computer sense. It's something stranger. Self-organizing information structure. Consciousness and cosmos as unified process. Reality as eternal present moment of actualization. The research continues. New experiments. Better theories. Deeper mathematics. Searching for signatures. For limits. For glitches. For anything revealing nature's source code. So far, nature stays silent. Reveals quantum weirdness. Shows relativity's precision. Displays mathematical beauty. But doesn't show programmers' fingerprints. Doesn't reveal external source. Just presents consistent, coherent, mysteriously fine-tuned reality. Make of that what you will. We're left with uncertainty. Maybe that's appropriate. Maybe reality is fundamentally uncertain. Not just practically unknowable. Actually indeterminate until observed. Potential until actualized. Simulation until rendered. If so, questioning whether we're simulated misses point. We are simulation. And reality. And consciousness observing both. The universe experiencing itself. Asking whether it's real. Finding no clear answer because question assumes false dichotomy. Real versus simulated. Being versus computation. Consciousness versus mechanism. These might be false opposites. Different descriptions of single underlying process. What remains certain, reality is stranger than classical physics suggested. Quantum mechanics proved that. Whether strangeness implies simulation or something else stays open. But the search reveals something valuable. Forces examination of reality's nature. Questions assumptions. Pushes physics toward deeper understanding. Whether we're base reality or nested simulation, we're still here. Still experiencing. Still conscious. Still searching for truth. That won't change regardless of answer. The quest continues because we're the kind of beings who ask these questions. Simulated or not, that makes us real enough. Perhaps the deepest insight isn't about simulation at all. It's about what we're willing to accept as real. For centuries, we assumed reality meant solid, external, independent existence. Objects occupying space. Following laws. Existing whether observed or not. Quantum mechanics shattered that picture. Showed us nature fundamentally depends on observation. Particles without definite states until measured. Reality malleable at smallest scales. universe that seems to care whether you're looking. That's unsettling. Violates intuition. Makes cosmos feel less substantial. More dreamlike. And maybe that's closer to truth than we're comfortable admitting. Not that reality is fake. But that solid, external, observer-independent existence was always illusion. We live in participatory universe. One where observation matters. Where consciousness plays role. Where physics and awareness intertwine in ways we're only beginning to map. The simulation hypothesis forces this confrontation. Makes us question fundamental assumptions. What is reality? What makes something real? If perfect simulation is indistinguishable from base reality, does distinction matter? If you can't tell difference, maybe there isn't one. Maybe reality just is whatever's consistently experienced. Whatever follows rules. Whatever consciousness engages with. This doesn't trivialize existence. Doesn't make life meaningless. If anything, it adds dimension. Suggests consciousness isn't accident. Isn't epiphenomenon floating on top of mechanical universe. It's woven into fabric. Part of how reality actualizes itself. Each observation, each measurement, each conscious moment participating in ongoing creation of what is. Whether you call that simulation or self-generation or participatory universe or something else entirely, the core insight remains. Reality is process, not object. Becoming, not being. Information organizing itself into experience. Consciousness and cosmos as unified phenomenon. You're not separate observer looking at external world. You're part of the world observing itself. That's the real revolution. Not whether we're simulated, but recognizing we're inseparable from reality we experience. The universe looking at itself through your eyes. Thinking about itself through your mind. Asking whether it's real through your questions. And finding, in that asking, the only answer that matters. You're here. You're conscious. You're experiencing. That's real enough. The rest is just details we're still working out. So next time you look at your hand, or the sky, or anything at all, remember this. You're not just seeing reality. You're participating in it. Helping actualize it through observation. Making it real by engaging with it. Whether that makes you simulated being in cosmic computer or conscious agent in self-organizing universe, the experience is identical. And the experience is all we ever have. All we ever will have. Make it count.